Hi folks, and welcome to an OALabs Patreon exclusive tutorial. Today we're going to be talking about the PEB. What is it? How do you access it? And most importantly, how do you identify when someone else is accessing it when you're reverse engineering some code? Now, if you're seeing this, it's because you're watching this video on YouTube. So just a quick shill for our Patreon. If you like this kind of content, go check it out. With that, let's jump in. So of course, I think probably everyone here has heard of the PEB. You probably know what it is. You've probably even accessed it yourself, written some code to access the is being debugged field or something like that. Most people are familiar with the PEB. And in fact, the Wikipedia article on the PEB, it's good enough. It explains what it is. You don't need a tutorial to explain to you how it works. What's different about this tutorial is we're actually going to open IDA and we're going to show you guys what it looks like from a reverse engineering perspective. Now, it's very different to understand what the PEB is and maybe write some C code to access it versus actually having to identify what fields are being accessed and what's actually being changed or read in the PEB if you're reverse engineering code. So that's what this tutorial is. It's understanding the PEB from a reverse engineering perspective. So first off, just what is the PEB? I think this, you guys are probably all familiar with Geoff Chappell. He has that fantastic blog where he documents many different Windows internals structures. I think he summarized it the best, so I just put his quote up here. The process environment block is the process's user mode representation, right? So it's basically all the information that you need to know or that the host, the computer needs to know about the process in user mode. Now, for this tutorial, like most of our OALabs tutorials, we're just going to stay in user mode. We're not going to complicate it with kernel stuff. So from a user mode perspective, this is basically encapsulating all that you need to know about the process or how to find that information. I think the best way to think about it is to think about it like a directory. That's how I think about it. I think of the PEB as a directory. If you want to look up information about a process, where do you go to find that information? So enough blabbing about it. Let's just look at it. Best way to understand something is just to look at it. So I just threw up a struct here, which defines the PEB. Lots of fields in the PEB are officially undocumented. And I have linked below a link to a website, Vergilius, I can't pronounce it.
Vergilius.
Which has all different documented structures from Windows internals for all different kernels, all different releases of Windows. And it has many of I think all of the undocumented fields in the PEB, an invaluable resource if you want to find out what these other undocumented fields are. But I digress. Let's just talk about the simple documented portion of the PEB here. So like I said, I think everybody's probably seen this before. Probably most people's first interaction with the PEB is the being debugged field. This is just a simple flag that is set when the debugger is attached to a process. And if you've done any of these like simple crack me's or simple debug me type challenges, one of the first things that the software will check this, being debugged flag in the PEB. So most of you have probably experienced the PEB from that perspective. There's also another field in here which is probably equally as important and equally as well known, which is the loader data or the loader pointer. And that's actually going to be the subject of the next tutorial. So we're going to talk about how to access modules that are loaded in memory from the PEB. But for now, you just have to know that the in-memory order module list is pointed to by this loader field here. So those are probably the two most common fields that people interact with first with the PEB. And like I said, we're going to be doing a deeper dive into that in the next tutorial. But for this one, let's just talk about how do you get to the PEB? How do you access it? So to access it, usually you'll be going through the TEB, the thread environment block. Analogous to the PEB, the TEB is everything you need to know about a thread. So each thread has something called a thread environment block. And just like the PEB contains a directory of information about a process, the TEB contains a directory of information about each thread. I don't know if they picked that up, that race car. That was interesting. I'll cut that out. And of course, if we're trying to access the PEB, the most important field in the TEB is the process environment block pointer. So you access the TEB, you find the process environment block pointer, you access the PEB from that, right? Now let's talk about how you access the TEB and some of the other stuff that's actually contained in it. So here's a nice diagram I stole directly off Wikipedia, but it's actually a really good representation of the TEB. So the first thing that you'll note about the TEB is this funny reference here, the FS and GS registers. So that's actually how you access the TEB. there is inside the CPU, there's an FS register on 32-bit and GS register on 64-bit, which will contain the address of the base of the TEB. So in normal CPU architecture, obviously it doesn't specify like the FS register is for Windows TEB. I mean, it's it's agnostic to the operating system environment. But on Windows, the FS register on 32-bit is dedicated to accessing the TEB. And on 64-bit, it's the GS register. So though that's just convention on Windows, that is always going to be true. And that is actually how you access the TEB. Now, you could access the TEB at FS0. So that's offset 0 from the value that's stored in the FS register, right? So that's the base of the TEB. You could do that, but it's much more common, especially when a developer is writing code, to actually access the base of the TEB via a pointer that is in the TEB. So there's a self-referential pointer that will point to the base of the TEB. And so oftentimes you'll see in code written like this, where instead of accessing FS0, they're actually accessing FS18 on 32-bit systems and GS30 on 64-bit systems. The reason for this is because then you can easily cast this as a pointer and you can begin accessing the fields within the TEB. Instead of having to access them by dereferencing addresses, you can access them nicely with nice little pointers from the PTEB struct. So that's why that's done. The important thing here, though, is that if you're doing this, you'll see in assembly code FS18 and not FS0. So that's an important thing to keep in mind. Also, I want to note something about the Windows intrinsic here, this read FSD word and read GSQ word. We're going to be talking about this a little bit more when we actually open some code and take a look at a simple example here. But I just want to mention that that is actually Windows intrinsics that you can use to access the FS and GS registers when you're writing code. When that's compiled, that intrinsic goes away. That's just for the Visual Studio compiler, and that is transformed into a FS register access. Okay, so now that we've covered off the basics of the TEB, let's talk about how the TEB is used to actually access the PEB, the core of this tutorial. So you could obviously access the TEB from FS18 and then dereference a pointer to the offset 0x30 to get you the linear address of the PEB. But most times you'll actually see the PEB address accessed directly. Just like I showed you for accessing the base address of the TEB via that linear address at FS18, here the PEB can be accessed via FS30. So this is actually probably one of the most important slides before we actually get into opening up IDA and taking a look at the code. This is because no doubt if you've done any reverse engineering at all with any sort of malware, you have seen FS30 in the code. GS60 if you're looking at 64-bit, but because a lot of people start with 32-bit, you've probably seen that FS30. In fact, FS30 is so common that it's sort of a meme within our reverse engineering community. As soon as you see FS30, you immediately think PEB. They're looking at the PEB. So all of that to say that you can access the PEB via the TEB, which is stored in the FS and GS registers for 32-bit and 64-bit, and at offset 30 hex and offset 60 hex for 32-bit and 64-bit. So basically that's how you're accessing the PEB from the TEB. And with that, let's jump into an example, and I'm going to show you a very simple example where the PEB is accessed to read the being debugged flag to determine whether the process is being debugged or not. So let's jump into that now. Okay, so for our demo here, we have very simple code open in Visual Studio. What we're going to be doing here is we're going to be reading the GS word at 0x60, and then we're going to be casting that as a pointer to the PEB and assigning that to our pointer to the PEB here. And then we're going to be accessing the being debugged field. We're going to save it into a D word. Now the being debugged field is a byte, but we're going to save it into a D word. Don't worry about that too much. And then we're actually going to print out the debug status. So if we're being debugged, I would expect this to print out a 1. And if we're not being debugged, I would expect it to print out a 0. So like I said, very self-explanatory. I also have a definition for 32-bit here with the read fs word 30, which I will compile and I will leave down below the video as an exercise for you guys. So let's take a look at this in action. It's already compiled. Okay, so we have our console open here and we're in the release directory. So if we run PEB, and we can see the debug status is 0. There's no debugger attached. Let's attach a debugger and see what happens. So here we're going to open up x64 debug, file, open, and we're going to open the shellcode PEB here, open it up. We're going to run until the entry point. We don't really have to worry about what's happening in the debugger too much. We just want to see what's printed out to the screen here. So what I'm going to do is under the options, preferences, I'm going to make sure there's an exit breakpoint here. So that means that we'll hold the window open once the debugger has exited. So I'm just going to run here. The debugger has exited, but we're still holding the window open. And you can see here the debug status is 1 because the debugger is actually attached. So incredibly self-explanatory, very simple example. Now let's pop open IDA and take a look at the code, and we'll see what this actually looks like when you're trying to reverse engineer something. Okay, so we have our code open here. We're in the main. We can see the first thing that happens, we make a little bit of space on the stack, and then we access that GS register at 60 hex. So that's telling me that right now an RAX is going to be our PEB, right? Then what we do is we load the format string, which is just what we're using to actually print that message to the screen. So we load that into RCX. And then we move the contents that are stored at RAX plus 2 into EDX. And this is what should give us our debug field. Now, of course, we could mark this up here. We could say this is the being debugged. And if you wanted to, you could also rename the variable here, right? If you wanted to, but that's not really what I wanted to show you in this tutorial. What I want to show you is how to mark up the pseudocode and make the pseudocode look nice. So let's F5 here. We're going to decompile. And you can see we've decompiled and things don't look right. They don't look good here. Let's split the screen and right click and synchronize. So we're looking at the same thing. Now, something is not right here at all. Now, before we get into this, I want to make it clear that I'm using IDA free, and I'm using IDA free so you guys can use the exact same version at home. With IDA free, the decompiler is cloud-based, so that means it actually makes a request to IDA servers to decompile the code. And because of that, we can't use the trick that we would normally use to fix calling conventions, which is to force IDA to decompile the entire binary. Now, if you haven't run into this before, this can be quite confusing. You might say, what's going on here? All of this important code that I thought would be here has disappeared. But really what's happened is IDA hasn't decompiled this function yet, so it doesn't know that it has the arguments wrong. And because it has the arguments wrong, the decompiler is ignoring or optimizing out a lot of the code that is actually required for this function. So if we were to double click on the function, we go into it, IDA now has had a chance to analyze it. There's a very important keyword here, which is VA start. That means that this is a variadic function. That means that it has an unspecified number of arguments. We've covered this in our calling conventions tutorial. If you're unfamiliar with what I'm talking about, I'd encourage you to go check that out now. So here we can see that this is a variadic, and of course, if you're familiar with C++ or C, you know that printf is a variadic. So once we go back to our, we'll just press back. Now that we have the calling convention correct, we'll press F5 again to decompile this. And you can see now that IDA knows there's extra arguments for the function. They have added this current PEB and then being debugged offset. So this is very straightforward. The assembly code is a little bit harder to follow because you don't have the nice struct definition, but in the pseudocode, it's very easy to see what's going on. This might not always be the case. There are some instances where you may not get a clean structure, and we're actually going to be showing you those much later on in a future tutorial where we talk about shellcode markup. And there's one last thing to note here. You might have noticed that instead of the Microsoft intrinsics here, the read_gs keyword, we actually have something else. We have this NT_current PEB. Now, this is actually just an IDA ease of use optimization that they do, where they replace any sort of recognition of reading the PEB with this function here. And NT_current PEB is actually defined in Windows headers, but it's not documented. This is actually just an IDA-ism. So anytime you see this, even though it is actually defined inside of Windows, it's not a documented function. And really all it is just a wrapper function for what we saw here in our code, which is to get the PEB from the FS register. So in a nutshell, anytime you see this, you know that you're accessing the PEB. It's self-explanatory. And then you're just accessing members within the PEB. All right, I hope you enjoyed that. And like I mentioned before, if you enjoy this kind of content, go check out our Patreon. Lots more reverse engineering tutorials like this one right there. Go check it out. And until next time, keep exposing the mechanics behind malware. Like and subscribe. I don't know. Do we still do that? You guys let me know. All right. Bye, guys.